want to welcome you to your first day of Calc class online. We're going to be starting in section 1.1 today. Get the dust off these, I haven't used them in so long. In calculus, we talk about basically three things: limits, derivatives, and integrals. And the author breaks the integrals up into two parts: definite and indefinite integrals. In this first chapter, which I really like, he takes a very grassroots approach to these, kind of non-calculus based. So this whole first chapter, you just get a kind of an idea of what these three things are in calculus. That's limits, derivatives, and integrals. And today we're going to talk about derivatives. We're actually going to talk about them for a couple of days. So you get kind of an idea of what each one of those three things are, and then as we go through the chapters, that's when we get into the heart and soul of calculus. So this is, and you do have to take notes, they are required. Make sure they're labeled just like I label them. This is section 1.1. And we're only going to be spending 1 day here. A lot of times we'll spend 2 days on a section, but this one's pretty short. And what we're going to be looking at today is a derivative, but I'm going to introduce that term later on. I'm going to start us off with an example. So there's example 1, and we are going to look at a door with one of those automatic openers and closers. You know, you push the button on the wall and it opens up and then it closes. So we're going to be examining a door with an automatic opener. So what happens with this particular one? When you hit the button, the door is going to open fast. It's going to slow down. Then it's going to stop for just that split second. Then it's going to start closing. And then it slams shut at the very end. So before I give you an equation for this, I want you to be able to give me a rough sketch of what you think this graph would look like if we were to put time on the x-axis. So we're going to call t is going to be our x-axis. It's going to be the time in seconds since you pressed that button. And then we're going to let d, which will be our y-axis, be the degree of the opening. Is it at 10 degrees, 20 degrees, 30 degrees, all the way up to how far wide it opens, at least past 90, I would think. And then it's going to come closed again. So we're going to have degrees from its closed position. So if I were to have you just kind of guess before I give you the equation what this graph might look like if this is our time and this is our degree in seconds. So time 0, degree 0, the door starting closed. I'll get that point for you. What do you think? Just take a guess on what you think the graph is going to look like. So take 10 seconds here. Give me a little sketch of what you think it might look like. So I'll be quiet. Okay, hopefully you tried something there. Okay, so if we talk about it opens fast, that means we need to get to a high degree right away. It's going to quickly open. So that's like an increase here. Then it's got to slow down before it stops. And then it comes closed again. And as it comes closed, they usually close slowly so they don't hit you in the feet on the way as it's closing up. So I would say something like closing. And it slams shut towards the end there. Something like that would be my guess. So if you came up with something like that, you did a pretty good job. Well, I'm going to give you the equation for this particular door opener. The equation is the degree of the opening is equal to 200 times t times, this is a time sign, 2 raised to the negative t. So that's 200t times 2 raised to the negative t. And our domain is how long it takes the door to open and close. And if you were in class, I'd ask you, give me a guess on how long you think it takes. This particular one, obviously 0 is where we're starting, takes 7 seconds from the open to the close. Okay, let's graph this on our calculators. And you will get pretty good at this. So go to your y equals where your equations are at. And we'll type that one in. 200x times 2 raised, and in parentheses, negative x. Okay. If I do a zoom 6, that's that 10 by 10. I'm not going to see a whole lot here. Seeing this over here, out towards the end, this is out at 10 seconds here. Oh, it didn't close up to 7. They're just giving us the domain to examine this out to 7. So we got to do some window changes. Okay, and you will get good at this window stuff. It takes a little while, but you got to think with some common sense. Remember, this axis is our degrees. I don't need any negative degrees, so I'm going to get rid of those. I don't need any negative time, but it looks like I need a higher number here on my degrees so I can see more of this graph. So I'm going to go to the window. My x is my time. I'm going to have that start at 0. Out to 10 is fine. I only needed to go to 7, but I'll go out to 10. X scale, that puts a tick mark at every 1 second. Now I'm into the y's, my degrees. I know I've got nothing past 0 degrees. 10, I know the door gets wider than 10 degrees, because if that was the case, I would not be fitting through it. So if I think 100 degrees, past the 90, the y scale, this doesn't matter. That's just going to put 100 tick marks on my graph there on the y-axis. I'm going to change that to like 10. So it'll put a tick mark at every 10 degrees. And now I'll graph. And you can see I still don't see the very top of this, and I guess I'd like to. So this is telling me that it's going past 100 degrees. I'm going to go back to the window. I'm going to kick that up to, say, 130. And there's a graph. I didn't do too bad. I knew I was steep at the beginning. It kind of swoops a little more than mine, but that was just a rough guess there. So let's put this sketch on your notes. Time in seconds. D is degrees. Jumps up. Slows down. Okay. Now my first question about this graph, call it question A. How fast is the door moving at 1 second? Okay. Okay, my question is how fast is the door moving at 1 second? So when you think fast, if you think about how fast are you traveling in the car, what kind of an answer do you give? So when that cop pulls you over, what kind of answer do you give when he says, do you know how fast you were going? Your answer you're giving him is hopefully something in miles per hour. So in this case, when I ask how fast is the door moving at 1 second, what kind of answer could you give me? Knowing that we are talking about seconds and degrees. Okay, so I'm looking for a rate in this context. And hopefully you could come up with, well, I could give the rate in degrees per second. So how fast is degrees? I'm going to use the little symbol for degree per second. That's the kind of answer I'm looking for. Well, if I go to my equation and I put in 1 second here and 1 second here, just plug and chug algebra, substituting in 1, the answer I get is not going to be a rate. And we can use our table feature, and you'll get really good at this too. I don't know if you've done this before, but we're going to go to table set. I want to start, because I want to plug 1 in, I'm just going to have it start at 1. It doesn't matter what I go by at this point. So now when I go and look at the table, so I did second graph to get the table. At 1 second, the y value is 100. So that one, and if I go back to the graph to see where that's at, if I trace, I could have done it here too. Trace to 1, hit enter, and it jumps to that point on the graph. Well, there's a couple ways to get our answer. See, it's right here on the way up. Right here is my 1 second, and my degree is 100 degrees. So, does that mean it's moving 100 degrees per second? Well, think about that. 100 degrees per second, that means that thing flew open and it was at 100 degrees in 1 second. No, that's not, no, I didn't say that right. Skip that. So what my point is, when I plug 1 in, all it's telling me is the degree that it's at. It's not telling me its speed at this point. So what we want to do is come up with a way to turn that into a speed. So what we're going to do is take another point very, 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 very close to the 1, like 1.01. So if I take a second point now, so if that's 1, I'm going to exaggerate it a little bit here. 1.01 seconds. So I've got 2 points that are very close together. Okay, I'm going to make a little table where I've got time and my degree. I know at 1 second it was at 100. At 1.1, I'd like to know that value. I'm just going to use this trace feature here. Trace, type in 1.1, and now when I hit enter, it jumps to that point on the curve, and down here it gives me the y value. So I'm at 102.63363. Or another way to do this, I can go back to the table set. I guess I want to show you both. I can make this jump by 0.1. So it'll start at 1, and then it'll go up to 1.1, 1.2, 1.3. And I can see the 102.63, but if I put my cursor on that, I get all the rest of the decimals. Because you're going to see with these problems, you're going to want to carry out a lot of decimal places. I think we're fine with the 5 that I wrote down, though. Okay, so now that I've got these 2 points, how can I turn those into a rate for me? Well, we talked earlier that it would be degrees per second. Per is you're just dividing. So what I want to do is take, well, how many degrees did it pass through from 1 to 1.1? All I have to do is subtract these 2 things right here. Not that I need to write it out, but just in case you're looking back. So I'm taking the 102.63363 degrees, subtracting the 100 degrees. That's going to give me how many degrees that changed over my change in time. So I'll get 2.633